2y j cross I, which is negative k. So this is what we get. So we get non-zero vorticity. So any point in the boundary layer except this point, any point inside the boundary layer except out at the wall will be rotating, will have a vorticity. And you can see it here from our cartoon that any point here, we have this guy, or this guy is moving with the same velocity everywhere, and this guy, okay? When we go downstream, this element is the same. Its omega is 0. Its angular velocity is 0. This line is angular velocity is 0. It's the same here. It just moves with the flow. This line, I'm talking about this line. So the 2 points, they move the same, right? But what about these 2 points? Which is faster? This guy is faster than this guy, right? So this guy will have a rotation like this. So the blue have a 0 rotation, omega is 0, but this guy will have omega b that is non-zero. So if you add them together, you get really a rotationality. Okay? Let's see some cool videos. Any questions before the videos? Yes, Anshan.
Does your boundary layer affect your circulation?
Yeah, we'll get to that. So here you can see immediately that the boundary layer has vorticity, right? Any boundary layer will have vorticity. So
another small question. Can an invasion flow have vorticity?
I'm sorry?
Can an invasion flow have vorticity?
Yeah, this is a controversial thing. Yes. Yeah, so inviscid and the irrotational, they are not exactly the same. One implies the other, but it's not the other way around. So where is this inviscid flow? Euler's equation, right? Still here we have rotationality. So the flow here can have omega, non-zero omega. Okay. Irrotation is something else. So yeah, back to Anshit's questions. So here is an airfoil. This is a good question. We have the flow. So inside the boundary layer here we have vortices. We have vorticity. So the vorticity distribution at each point in the boundary layer we have vorticity. Okay. And the same downstairs here, but it's in the opposite sense. Okay. So we can actually approximate. Thin boundary layers by sheets of vorticity. Okay. And jumping ahead, it's actually the vorticity in the boundary layer here in the lower surface that forms the starting vortex. Okay, so the starting vortex comes from the vorticity in the boundary layer on the top, on the upper surface, and the lower surface. We will come to this later. Okay. Any question about that? Any question? Let's see some videos. Yeah. Okay. This is a video by Shapiro. No, he is a playground. Yeah.
The two veins at the bottom.
No.
This gadget.
Oh yeah. Okay.
This gadget is a vorticity meter, which floats in water with its axis vertical. The two veins at the bottom are driven by the angular velocities of two mutually perpendicular fluid lines. So the arrow at the top turns at a rate equal to the average of these two. That is, with half the vertical component of vorticity of the lump of water in which the veins are immersed. This tank has been on the turntable for a long time, and viscosity has forced the water into a rigid body rotation. The vorticity float rotates almost exactly with the speed of the crossed white lines at the bottom of the tank.
Yeah, this is example one, okay? So you have the vorticity meter is something that rotates with the average of the two lines, you know? They have two perpendicular lines. Our vorticity omega is the addition of these two, so if you get the average, it's just half of your omega, okay? So this guy, the arrow, just rotates with the angular velocity equal the average of this thing, which is half of your omega. This guy is rotating, you get an indication of how much vorticity. So here it's exactly rotating with the table. So it's rotating with the same angular velocity. Let's look at this example.
That water flows in a straight channel. The streamlines are essentially straight and parallel to the side wall. But the arrow rotates, showing that vorticity is present.
You can see that the fluid particle is rotating while moving straight. The streamline is just straight forward, right? This is a flow near the wall. If you get it outside, you will not see rotation. And vice versa.
This is the plan view of a spiral vortex tank. Water passes from the reservoir through a flow straightener and into the tank through a tangential entry. It spirals round and round in a very tight vortex and finally leads vertically through a drain in the center. What will the vorticity meter do? It doesn't rotate. It moves in pure translation, like the needle in a compass box mounted at the rim of a rotating turntable.
So though the flow is curved, and we indeed have circulation here, but the fluid particle itself just moves with the same orientation, doesn't rotate. Okay? Any question? Okay, so exit the cool videos and go back to the demonstrations. So we refuted this, saying that curved flow does not imply vorticity, and we just learned that it's the other way around. Also, vorticity does not imply curved flow, right? So here we have vorticity in this straight flow. Where should I write it? Maybe vorticity does not imply curved flow. Any question about that? So we characterize, we spend quite a time with vorticity because it's very important. Any question? We'll now go to the relation between vorticity and circulation, and it's very straightforward. So circulation anybody remembers the definition of a circulation? Was what? Integral over closed surface of u dot dx, right? Actually this, without anything, just pure math, by Stokes' theorem, any vector, any line integral, a closed line integral, of a vector dotted dx, whatever this vector is. So we have here, this is on a closed contour C. It's the double integral over the area, the enclosed area. The double integral over the area of nabla cross this vector, whatever this vector is. If it's u in our case, then it's u here. Dotted with the normal, the unit normal. This is the unit normal of the area. D area. So Stokes' theorem, it converts the line integral on the boundary to an area integral. Okay? And to us, what's this guy? This is vorticity. So this is the relation between circulation and vorticity. It's simply integrate your vorticity over the area. Okay? Integrate your vorticity over the area. Any question about that? So let's do it for the example one that we have. example 1, we had the flow was completely tangent, the rigid body thing, omega r in the E theta. Let's do it from the basic definition of circulation. What's the basic definition of circulation? Let's take a circle, okay? So I'm gonna integrate over the circle, over theta, from 0 to 2 pi. This is a closed contour, right? What you're gonna integrate? I will integrate the velocity, which is omega r, times the line element. The line element is r d theta, correct? So here you get omega r squared, and the integral of d theta from 0 to 2 pi is just 2 pi, okay? Now we can do it from the other way around. It's the integral over the area, over the circle. So what's the area element? Anybody remembers the area element? What's the area element? dx dy, if you are Cartesian, if you are cylindrical, what's the area element? r d theta, right? And we are integrating here the vorticity, okay? The vorticity, anybody remembers how much the vorticity was? In this example, the rigid body with omega, large omega, what's the vorticity? If you have rigid body rotation with large omega, what's your vorticity? It's just 2 omega, right? So our r is from 0 to r, and our, maybe we can have this as large r just to prevent confusion. So this is large r, and our theta is from 0 to 2 pi. What we get here is 2 omega, r dr is r squared over 2, and d theta from 0 to 2 pi, we get just 2 pi. So we get the exact same thing, right? Either from this definition or that definition. Okay. Let's see here. I have an airfoil. Let's take a closed contour here, a small closed contour. So the velocity here is u, your velocity distribution. And here may I have v and v plus dv or something. And the velocity here is how much over the airfoil? How much is the velocity here? How much is the velocity over the airfoil? 0. Okay, so let's compute the circulation over this little contour. So I'm taking a teeny element. What's the circulation? We're going to do it like last time. So this v times the line element along it, so it's v dy. This u times the line element, so it's plus u dx. Then this velocity times negative dy, because I'm doing this along a closed contour, so I'm moving like this, like that, then like this. So this is negative v plus dv times dy. Then the last element, it's negative, but it's actually, I have 0 velocity. So this is what you can see, that v dy with v dy goes away, and you end up with dv dy. This is a higher order term, so this is almost u dx. Okay? So if I introduce distribution of your circulation, what's the circulation? The circulation is a global measure of rotationality. So the flow here in this region, enclosed by this contour, has this much rotationality. I can opt to distribute this circulation, okay? If you introduce a circulation distribution little gamma, function of x, the relation would be, of course, from 0 to c gamma of x dx, right? Or in other words, equivalently, gamma is the same thing, right? Large gamma will be little gamma dx. Or little gamma is d large gamma by dx. What I'm trying to say is that your u, as a function of x, your velocity distribution over the airfoil can be approximated as your circulation distribution. But this is if I'm just focusing on the upper surface. If I'm focusing on the difference between the upper and lower surface, if I have a very thin plate, and I have here U plus delta U, and I have there U minus delta U. So actually, the relation would be the half effect. So this will be twice delta U will be your circulation distribution. And this is a very essential relation in thin airfoil theory. Okay? So lift is mainly due to circulation. Circulation is actually comes from the area integral of vorticity. The vorticity reside in the boundary layer. So the lift in some sense is due to the vorticity in the boundary layer. Okay? So the lift production is essentially a viscous process. The boundary layer, which is a viscous thing, can be represented by a sheet of vorticity. The boundary layer, to us now, can be represented like this by a distribution of circulation. So whenever you see this thing, even in an irrotational framework, in a potential flow framework, it accounts for viscosity in an indirect way, because this distribution is very related to the vorticity distribution in the boundary layer. Little gamma is not exactly the same as omega, as the vorticity, but they are related. Okay? This is circulation per unit length, but gamma is circulation per unit area. Okay? They are a little bit confusing, but hopefully you digested well. Any question? We're done with today. 5 minutes earlier. I'll take next time. Any question? Any question? Maybe we can motivate the next lecture in a couple minutes. Any question, please? If you have any questions. So what did we do today? What did we do? We introduced this the local derivative, the convective derivative. Hopefully we digested this well. We introduced the scaling. We talked about the taxonomy of Navier-Stokes equations. We have some exact solutions versus this is what we're interested in, because we want to do more complicated problems, approximate solutions. This is what we're interested in as aerospace engineers, but unfortunately this approximation is not very helpful. Okay? Then we learned about vorticity and rotationality. We learned